بسم الله الرحمن الرحيم الحمد لله رب العالمين والصلاة والسلام على أشرف المرسلين. Good morning, ladies and gentlemen. We welcome you in the first lecture of this morning session by Professor Evan Barkins. PhD studies were in main group synthetic chemistry, and that produced 20 publications in international journals. Postdoctoral study was in metal multiply bonding chemistry and produced 10 publications. He then changed research fields entirely and moved into materials science and pioneered a new research field of solid state metathesis. He has very long, honestly, CV, but to cut the long short, he has involved in the development of a new nanoparticulate antimicrobial agents and strong interdisciplinary interactions with microbiology. In 2010, he developed a new visible light photocatalyst and showed that they were outstanding at photo-splitting water. He is the author of some 375 international research papers and has given over 150 invited lectures. He will be talking about super hydrophobic surfaces, taking a leaf out of Nature book. Please, Professor, the floor is yours.
Thank you very much. So, first of all, I'd like to thank the organising committee for inviting me along to give a talk to the beautiful city of Jeddah. I understand there's been no rain here for 3 years, so now I've managed to arrive a day when the rain did come, which is very apt for this particular talk, because we're going to talk about super hydrophobic surfaces. Now, this talk is very wide-ranging. I'm going to cover a very large number of different areas. Mainly it will be about super hydrophobic surfaces, but I'll include quite a lot of other aspects as well, including explosives, commercial coatings, a whole range of things. I guess the claim to fame for me is that I helped to develop the world's first self-cleaning glass. So this is called Pilkington Active. This is the glass that cleans itself by the action of sunlight and rainwater. It's a very thin coating of titanium dioxide. And I first started work on that in 1996 in our lab, and we worked together with the company and we helped to commercialise that product. That product's now worth about £500 million a year. I don't get any money from that, but they do sponsor my research, which is very good. So I'm going to talk about a whole range of things. I'll talk about fluorine-doped tin oxide and doped titanium dioxide. I'll talk about the super hydrophobic surfaces in the middle of the talk, and most of it will be related to this. And there's quite a lot of videos at this point, so if you're going to fall asleep, you'll wake up when the videos come in. I'll say a little bit about work we've been doing on zeolite gas sensors for detecting trace gases for explosives, because we work on forensic detections. We also do work on functionalized gold nanoparticles, so I was very interested in the plenary lecture that came on. And also we do work in organic chemistry on magnetic hypothermia. I've got about 6 other research areas we do, but I'm going to try and cover some of these. The first one's related to tin dioxide. Tin dioxide on a window surface is used to make what's called a solar control coating. It's no good for this country because it's too hot, but in the UK where it's cold, these solar control coatings help to reflect heat back from a window into the building and keep the building warm when it's cold. And so this is based on tin dioxide, of which the structure is shown there. And we do the deposition by a process called chemical vapor deposition. This is where we have molecules in the gas phase, they come down onto a surface, the surface is hot, and typically we do depositions at 500 degrees C to 700 degrees C, but in industry, when you're manufacturing glass, this process is done on a reel-to-reel process. There's a ribbon of glass which is about 3.5 meters wide, 1 mile long, and that's coated as the glass is manufactured. In particular, we've looked at a process called aerosol-assisted CVD, where we use an aerosol as a delivery vector for our starting materials. And there are 2 ways in which we do that, either with an ultrasonic humidifier or with a collision atomizer. In fact, if you've had a little spray this morning, you would have used something which generates an aerosol. That's essentially what comes out. You have an aerosol gas. But we use this aerosol So we pass gas through the aerosol, we transport the aerosol droplets to the reactor where the aerosol evaporates and we generate our thin film. These are a representation of what our apparatus looks like. Our precursor chemicals we keep in these, what we call bubblers. These are heated jackets. So the gas comes in, goes through this, gets enriched with whatever chemical we want to put in, goes through the pipework and then goes into this, which is our coater. So this is the representation that we do. We sometimes scale things up to about 1 metre to make coatings, and when we do it industrially, we do it on a metre wide ribbon, about half a mile long, on a rolled glass line. For making titanium dioxide, we use titanium tetrachloride, ethyl acetate, and sometimes we put some nitrogen dopant into the system. And essentially, as the gas comes in, we get deposition on our glass substrate. So this is our reactor. Have a look at this reactor. It looks nice and clean. I'll show you later on what happens after various runs. And we've deposited our fluorine-doped tin oxide films. We use monobutyl tin trichloride as our starting material, and we use trifluoroacetic acid as a fluorine source. And our depositions were done between 350 and 550 degrees C for about 30 minutes. When we do that, we produce very nicely crystalline doped tin dioxide films, and this is called a texture coefficient, which gives rise to how much preferred orientation you have in the film. When you look top down, this is what they look like. And they have this pyramidal microstructure. Now that's absolutely ideal for solar cell applications because you want to scatter the light into the solar cell. And these films are used for solar cells very, very widely. So when we did this, we can make films between 500 and 800 nanometers thick. It has high surface roughness, and the haze values we get from the films is around 8%. The ideal haze value is between 6 and 12%. So we're almost at an ideal haze value for photovoltaic applications. Now these are the key numbers, and this is why this is important for what we've done, and that's the sheet resistance of the film. Hello. Oh, we're not on. Sorry. Is that better? Yeah. I couldn't hear upstairs, I don't think. So So when we do that, and we look at the sheet resistance, we get sheet resistance values of around 2 ohms per square. To give you an idea, the best commercial products are around 10 ohms per square. So we can make with this product, or this methodology, a better material than is available commercially. So at the moment, we're looking to scale this up with industry. In particular, we get quite high mobilities for our films. So the sheet resistance is made up of mobility and charge carrier concentrations, and ideally you want a high mobility, and that's what we get from these particular films. These are the optical properties. So over the visible region, we have very high transmission, which is absolutely ideal. This is what you need for a window coating. However, when you look at the reflection, usually we move the plasma rays towards the visible, which means it's a better performing material. This also shows another example where we're comparing our film, which is this line here, with a commercial product, and we're getting better overall results. So when we do that, and we compare it with the commercial product, so this is Tech 8, which is produced by NSG, and this is Asahi U glass, then we're getting overall better sheet resistances. We get to about 4 to 5 ohms per square, whereas the commercial products are 15 to 28. So we get better transmission, better overall products, and we're looking for commercialisation of this. The doped titanium dioxide study is actually work we've been doing with King Abdullah Aziz University here in Saudi Arabia, in particular when we've looked at tantalum doping into titanium dioxide. And what we wanted to do here is to make a coating which works in 4 different ways. That it could act as a photocatalyst, it could act as a transparent conducting oxide material, and then it could also act as a blue-coloured tint for our glass as well. So we looked to see whether we could do that. And the way in which we did it is that we combined these chemicals together by aerosol-assisted CVD at around 500 degrees C. And when we do that, we've got a little subliminal message there for the university behind. Putting niobium into the lattice, we can generate this beautiful blue colour. It hasn't come out very well on this particular screen, but a beautiful blue colour where we have doped niobium into the titanium dioxide lattice. And we can see as we put niobium in, we get a Vegard's law relationship in terms of the parameters increasing. When we look at the metric properties of the film, again they've got these nice, this nice microstructure. which is what you need for a solar cell application, and we can get down to about 6 ohms per square, which is better than the commercial product, which is around 10. Very unusually for this system, when we do the doping, we found that it's the titanium that gets reduced. So by doing XPS analysis, we find the blue colour comes from a small amount of titanium 3+ in our material, not from a reduced niobium 5+ to niobium 4+, which is what people have used via PVD. So this CVD method seems to give us some advantages. We also show that it works as a photocatalyst as well. So not only have we got the colour, we've got transparent conducting oxide properties, it also works as a photocatalyst. And this is where we're degrading a film of things like glycerol or hydroxycellulose and things like that, as well as stearic acid. It's not as good as a commercial product, but this commercial product doesn't have a colour and it doesn't act as a transparent conducting oxide. So we combine together 3 properties in this film. Now I'm going to go to the major part of this talk, which is related to hydrophobicity of surfaces. And so what we've done is that we've created a series of films which are super hydrophobic. Now for a hydrophobic film, this is the way in which you define it. It's this angle here that's tended at the surface of the droplet. So when this angle theta is greater than 90, the water droplet starts to form more of a marble type shape, more of a round sphere as you go to higher contact angles. And so we've looked at this and we've made a series of surfaces where we induce a surface roughness and a low energy surface. To be super hydrophobic, you need a contact angle here greater than 150 degrees. Also, things which are important are the tilt angle. That's the angle which you need to tilt the film up before the water droplet starts to move across the film. And there's also 2 other terms which are the advancing and receding contact angles. That's the advancing and that's the receding one. Now this is something which we discovered, we published in ChemCom a few years ago, is that if you look at the static water contact angle and then you drop the water from a height from the surface, we found a linear relationship. As soon as you hit the super hydrophobic mark, the water starts bouncing on the surface. And the more super hydrophobic the film, the greater the number of bounces that you will see on the surface. Now this is important for self-cleaning applications. We also found that the surface microstructure was important as well. If you have a rounded microstructure, you start clicking into the bouncing at 150 degrees. If you have sharp microstructure, it starts clicking in about 155. And if you have needle-like microstructure, it starts clicking in about 167. And what I'm going to show now is a series of how water interacts with surfaces when you put water, dropping it onto a surface which is super hydrophobic. Now the first one is this video. And this video will show an example of, oops, I've just gone one too far there, show an example of the Lotus effect. And that is, when you have water on these super hydrophobic surfaces, the water doesn't slide, it rolls. And that rolling action is really important. Now the way we did this is put a little bit of glitter inside there, which is my daughter's idea. She was 11, we had some at a Christmas party, and she said, why don't you try this? So we did, and it worked very, very well. Now, the rolling action enables the water to pick up dirt, bacteria, viruses which are on the surface, and to clean the surface. So if you can make a rugged super hydrophobic surface, there are huge number of potential applications. Now this is my favourite, or one of my favourite videos. This is what happens when we drop water droplets onto different surfaces. This has a contact angle of 150, 1 bounce. This has one of about 160, there were 2 bounces. This one has a contact angle of about 170, there are 6 bounces on this surface. And this one, which is the champion, has a contact angle of 175. And you can see, if you were bothered to count, there are 13 bounces on the surface. The other thing with these surfaces, they're a very good way to check if you've almost got an atomically flat surface as well. Because it's really difficult. Oops, it's really difficult. Oh, we'll have to play it again now. It's a shame. Just do it once more. It's really difficult to keep the water droplet stationary on the surface. It took us about 20 goes until we could get this in the frame, because it literally just shoots off left or right, even just a tiny, almost microscopic tilt, and it rolls. So this is our water bouncing system.
Can I interrupt?
You can interrupt.
Which determine the number of bounces?
The number of bounces is determined by the static contact angle. So the more marble-like it is on the surface, then the more bounces that you have. And so the way we do that is to control the surface microstructure by making it rough and also having a water-repellent surface. We have a polymer surface which hates water. By combining the polymer surface which hates water with the roughness, we get the bouncing.
Has nothing to do with the thickness of the
No, nothing to do with the thickness whatsoever. Right, this is a quick video, this is speeded up, and it shows you how you can make paper completely water resistant. So what we do is that we've added here a coating, and we use 2 scales of titanium dioxide particles on the surface, and we just put it onto filter paper. We quickly dry with compressed air. This is 6 times the normal speed. The whole video takes 2 minutes, but it takes quite a long time to look at it. So this, within 2 minutes, we've completely converted this paper, it's filter paper that you'd use in the lab to absorb water to make it water repellent. So let's put the water droplets on. The bit that's been coated, the water droplets just run off. They won't stay on the surface, but this other part over here, the water droplets, which it hasn't been treated, will just seep into. We've actually done this for a whole range of materials now, not just for paper. You can move to other materials. And these are further, so first of all, this shows you what it looks like on an untreated material for glass, for steel. I think we're going to have some paper coming in, and cotton. So cotton, if you just drop water on there, it just absorbs into the surface. What we've done with our treatment, we can coat virtually any surface now with our super hydrophobic coating. And this is work which we published in Science earlier this year. When we do that, the water gets repelled from those surfaces and just bounces off. So that's what happens on glass. You can see, well, I've given you a demonstration of that already. Similarly on steel, for the coated surface, it does the same. Even the little micro droplets run off. And the very surprising thing, we can do it for cotton. Right? So we are talking to a number of men's and women's wear manufacturer for clothes to have clothes which won't absorb water when you go out in the rain and will shed themselves. Waterproof, essentially, yeah. So we've looked at those systems. I've just got a couple of more videos while I'm on video mode. I'll get this one to play. No, that last one didn't seem. Let me just have one more check, see if I can get that to. Oh, here we go. So this shows a dirt removal test. So this is a super hydrophobic surface, and on that surface you see another water droplet, and this is simulated dirt which we put down. I talked about the rolling motion. This rolling motion of the water droplet acts as a miniature vacuum cleaner, and it sucks up all of the dirt from the surface, and you can see that there's a clear path afterwards where the water droplet has moved. So this is really good for being able to clean dirt. And in fact, this is what nature does. This is our taking a leaf out of nature's book, because nature does exactly this. It cleans itself for the lotus plants, for various other insects, for moth wings, for butterfly wings, for birds' wings. All of them have this super hydrophobic property where water will form a ball on the surface and roll. And that rolling motion helps to clean the animal world and the plant world of dirt and contamination. What we've done is managed to replicate this. But in particular, the big step change for our work is that we have a flexible layer underneath some of these coatings and then a rough layer on the top. And what has stopped commercialization is that the super hydrophobic coatings are very mechanically weak. And so if you go on the surface, you can blow them off. If you get tissue and you go like that, you could rub them off. But our coatings will actually survive many cycles of sandpaper. So we get sandpaper, we put it on the surface, and we can do over 100 cycles backwards and forwards with a high weight or the heavy weight on the surface, and it still functions as a super hydrophobic material. Now, one other area that I just wanted to mention while we're talking of videos is we're also looking at water splitting. And the idea here is that you use sunlight on a photocatalyst surface to split the water into oxygen and hydrogen. We had a paper related to this membrane which was published in Nature Materials 2 years ago and has had nearly 300 citations so far. So we've kind of worked out what is the optimum ratio for anatase and rutile forms of titanium dioxide to make the world's best photocatalyst. And we've then incorporated these material into the photodiode. So the way it works, we have sunlight coming in, The sunlight hits the surface of the titanium dioxide. At the surface of the titanium dioxide, it creates an exciton if you're a physicist, or an electron-hole pair. This electron goes over to this side through a membrane, and it causes photoreduction of water, generating hydrogen. And on this side, we get the photooxidation of water producing oxygen, and they're produced in two different compartments. So you could potentially use the hydrogen as an energy source, and use sunlight to do it, and using water as effectively as a transfer vector. So this is a video which will show that. So this is us shining light from this side. So when we got the light on, you can see the bubbles. Those bubbles are hydrogen, and you know it's hydrogen because they come on the other side from where you're illuminating. This is the photogenerated oxygen in a sacrificial system, and we have the light coming on this side, we have the oxygen coming out from the other side. We turn the light off here, the bubbles stop, so we get no hydrogen produced. Turn the light back on again, all the bubbles for hydrogen start. So this is a potential way of producing quite a robust material with long lifetimes to be able to look at photosplitting of water. Now we've actually made some demonstrator devices related to this, where we have a monolithic cell, the little logo down here, but this cell is about so big, which can actually photosplit water. Oops. So just moving on to the next part of the talk, we also have work which relates to metal oxide gas sensors. And the laboratory which I've taken over, this wasn't my work, have made sensors which are in 10% of all new cars. So if you buy a new car, you've got a 10% chance you've got a sensor that came from our lab. Well, not my lab, the lab I've inherited. These are called metal oxide sensors. They're very, very small. They're about 2 millimeters by 2 millimeters in size. And on the surface, we have a metal oxide which changes its electrical resistance with time. This is a UK 5p piece, which is about that big. So that's a centimetre scale. So it's very, very small. And we've done that to look at explosive detection and for forensic science. And in particular, to try and detect improvised explosive devices, landmines, and things like that, by sensing very, very, very low trace levels of gases in the air which are associated with the explosive materials. We've looked at actual explosives themselves, but we've also looked at potential explosive markers like ammonia, DMNB, nitromethane, and things like that. We've also looked at it for microbial threats as well, to see whether we could detect ethanol, which is a byproduct of a number of these microbial fermentations. So looking at things like influenza or potentially a microbial threat, a warfare threat. The way in which we make our sensors is that we have a screen printer, we have an infrared drying lamp, and we have a spot welder which we combine together to make the sensors. We do all our own in-house sensing. These are the rigs that I inherited. Sorry, we built this one and these two I inherited. This is called Sparky rig because it often gives people a shock. But we put the little sensor materials in. We can do eight gases at a time. And in particular, we add zeolites to those gases, to those sensors. And if we put a layer of zeolite on the top, they can give us gas filtration and also improve sensitivity. And this just shows some of the results related to ethanol, where we can see quite easily around 2 parts per million of ethanol with a pulse. So this is where we pulse the ethanol in. You can see a change in resistance. You turn the ethanol off, it returns to the baseline. And you get a pulse which is proportional to the concentration of ethanol. We've also done this with different metal oxide powders and shown the same. We've probably tested about 20 separate gases. We've even looked into looking at precursors for narcotics and narcotic detection, and we've also looked at explosive materials as well, including dinitrotoluene. The last parts of the talk, I'm going to talk a little bit about functionalized gold titania surfaces for antimicrobial coatings. And the antimicrobial coatings are important because in hospitals in the UK, in fact hospitals across the world, every time you go into a hospital, you have a high chance of getting a disease. You have about a 1 in 10 chance of obtaining a disease from the hospital when you go in. And if your immune system is weak, that can actually kill you. We have big outbreaks in the UK of things like MRSA, E. coli, C. difficile, and these cause deaths for people. So what we try to do is to come up with surfaces which will kill bacteria. So relating to the work we've done with titanium dioxide particles, we combine that together with oleic acid to make these gold cap nanoparticles. And when we've incorporated those gold cap nanoparticles, we showed that they act as a photocatalyst and also they can be used to kill bacteria. Now this is using UV light irradiation, but we've also got systems which work with visible light, and this is the kills against Staphylococcus aureus. So basically this is our control numbers here, but when we add the light we kill it. The very surprising thing for these coatings is that they work in the dark as well, so they give us some kill without necessarily having light activation, and that shows what it's like against the gram-negative. We've also looked at commercializing this, and this is an example of a catheter, and that catheter, which is the number one, catheterization is the number one procedure in all hospitals throughout the whole world, whether it's in blood, for urine, whatever, but this is the number one process. And we have, what we've developed is a laser fiber which goes inside the catheter. This has our light activated agent, and when we turn the light on, this actually disinfects the catheter and stops people getting catheter-related infections. If you are a catheterized patient, you have a 10% chance additive every day of getting an infection. So if you've been catheterized for 10 days, you will have a hospital-acquired infection. That can be treated with antibiotics, but there are less antibiotics available at the moment because there's so much resistance been developed by bacteria. So this strategy tries to prevent people getting infection in the first place. We've worked together with a company called Ondyne Biopharma, and they've developed these diffusers which can be used in the nose to disinfect people prior to going to hospitals. 1 in 4 of you will have an MRSA infection in your nose. It can stay there, you're relatively healthy, but 1 in 4 people in this room will have that. It lives at the space called the anterior nares, which is between the hard and soft part of your nose. Now if you've got that and you're an immune suppression patient, that could be very dangerous in a hospital. But if you use these diffusers with this blue dye, then that can actually get around that. The last thing I want to talk about is something we've looked at for healthcare, in particular to try and make metal oxide nanoparticles for use as anti-cancer agents. It's potentially a new way of treating cancer by using magnetic hypothermia. And the way in which this works is the magnetic nanoparticles go into your body, you can apply an external magnetic field and you heat the nanoparticles up. If you can localize those nanoparticles in the region of a tumour, then that can help to kill the tumour. Or, which we've looked at, if you can tag the iron oxide nanoparticles with a cancer recognition fragment, they will swim in the body to the point that you want to localize, and then you can apply the external magnetic field and kill the particles. What's particularly exciting about this is it could also be useful for secondary cancers as well as primary cancers. Now I had a student, Joe Bear, who was very keen to make these materials, and he wanted to do it just from basic household ingredients. And so we went, rather than going to Aldrich or a chemical catalogue, we went to a local supermarket called Sainsbury's, and we bought soap, olive oil and shark liver oil tablets, and then we combined them together. And this is the normal synthesis which people would do at 320 degrees using octadecane to make these iron oxide materials. But instead of using iron chloride, we used iron tablets from the high street. We use the basic soap, olive oil and shark liver oil. And when we do that, we can repeat those steps, and we can also generate our iron oxide nanoparticles, which we then characterize by a variety of techniques, including X-ray diffraction. And then we tested them for magnetic hypothermia. And that is, do they give a heating effect when put into an aqueous environment? And yes, we showed that we can get up to 2 degrees centigrade rise, which actually in some cases is enough to kill specific cells. So that's our shark liver oil. These are the things which we've looked at. Just to finish on, I'd like to acknowledge a number of people who've done the work. So Dr. Kafasaz, Bachu, Neumark, Noor and Bear have done most of the early part of the work. We have had a long-term collaboration over the last 3 or 4 years with Professor Mohammed Mukhtar, Salim Bawakid, Professor Salim Bashal, Abdullah and Shahil Daibati, related to a series of projects, in particular some of the transparent conducting oxide things I spoke about earlier. And I'd also like to thank NSG, Pilkington, Aeroqual and EPSRC and BBSRC who provided the funding. And also thank you very much for listening to my talk today. Thank you.
Thank you very much, Professor Bahir.
For your very informative lecture. Now the floor is open for questions. Yes?
It's a very interesting lecture, so I very enjoyed it. especially the superhydrophobic one, that as well as the hydrogen generation one. So I think this two is a separate project, I guess, right?
Yes.
So, and then for the superhydrophobic one, what is the transparency of your material that if you coat it?
At the moment, it doesn't have very high transparency.
Okay.
Well, actually, no. We've just in the last 3 weeks made one which is completely transparent. It's based on silica. The previous ones which we've done are all based on titanium dioxide, and they tend to be quite opaque. But what we've done is we've developed a paint. So we've made a super hydrophobic paint that you could, if we can scale it up, potentially paint onto your wall and make things super hydrophobic. So that would greatly resist any staining that you have for the surface. So at the moment they're quite opaque, but we have applications for opaque coatings, in particular for walls and things like that.
So, except the titanium dioxide, what is the other polymers they're using? Is that the...
So what we use, we
resin?
typically use a fluorinated polymer, which we have the titanium dioxide, which we coat with the fluorinated polymer. But we typically, for the titanium dioxide or the silica, we have to have 2 length scales for the nanoparticles that we use. So we have very small ones and slightly larger ones, some around 10 nanometers, some around 100 nanometers. And by having different length scale nanoparticles with a fluorinated polymer coating, that gives rise to superhydrophobicity. So you need a combination of all those. And we do it on a flexible substrate. So we can do it either on sticky tape, or we can do it on spray masks, or we can do it with some commercial adhesives. And it's a combination of all of those that gives us the ruggedness and the superhydrophobicity.
So what will be the crosslinker? Do you use any crosslinker on that?
No, there's no crosslinker. The polymer's already set when we put it in. So we're not doing a polymerization process as we're doing this. You can use oleic acid, for example, if you like, to cap the particles as well, or you can use stearic acid. We don't look at actually polymerizing the whole surface.
I'd like to ask about the solar hydrophobic material. How green is it, and is it removable?
How
How
green?
green is it?
Green. Well, that's quite a good point. I think when we're using the fluorinated polymers, that's something that people resist using industrially, but it is used because it does give a good effect. So the actual nanoparticles we use are actually fairly green. They can be made very easily of a relatively low energy process. It's the polymers which are not necessarily the green part. And you had a second question. What was that?
Yeah, is it removable?
Is it removable? You can remove these materials, but they are quite rugged, and that's what we've designed them for. But we have made systems where you can just dissolve by adding a different solvent. You can actually dissolve everything up. So you can use both acid and base solvents to be able to remove them if you want to. But we've tried to make things which are much more rugged, and we want them to be the marines of the coatings world. So they'll stick on, and they will work for a long time. But if you want to remove them, you can.
Interesting, thank you.
Thank you.
Any questions from ladies section? No questions from ladies section?
Yes.
Yes,
I
please.
have a question about the super hydrophobic materials. You mentioned something about the roughness of your surface. How much is roughness of the surface?
Roughness is absolutely critical on the surface. If you have just a flat planar surface with no surface roughness, the highest contact angle you can reach is 120 degrees. But if you roughen the surface, when you roughen the surface, you go to extremes. So something which is hydrophilic becomes super hydrophilic, and something which is hydrophobic can become super hydrophobic. So you need to have the roughness. Typically, the roughness wants to be on the micron scale. But we've used nanometer scale, but it needs to be at least that kind of scale to be able to use it.
You answered my friend's question, but also I want to add something else. If for example, pH of the water changes, how this surface behave? How is the surface?
For which one? The super hydrophobic ones.
Yeah.
The super hydrophobic ones. You can use them as long as you're not at sort of pH less than 1, or you go to pH 14 or 13.
Mm-hmm.
They're fine. They last for a whole range of different things. One thing we're using them for actually is for oil-water separation. So we make membranes which love oil but repel the water. And so if you have an oil-water mixture, or even just for straight chemistry, I'm the head of the department at UCL, and our undergraduates now use these as filters. All of you as chemists would have probably at one stage or another done a separation from an aqueous layer to an organic layer, or vice versa. And you always struggle at the interface. But we have a filter that will let all the organic part go through and keep all the water. Even if it's coloured, you can't see it, and it works really, really efficiently. And that's using the superhydrophobic coatings. The applications are enormous. If you could put them onto a boat, for example, you can reduce friction, so the boat would have less energy as it goes through the water, so it will reduce shipping costs. If you're trying to ship oil or water from place to place, if you put these on the surface, then you reduce the friction between the two surfaces. One further thing we've moved on to is a coating called a slips coating, where we put a polymer, this time related to your question, but we put a polymer down in association with our rough surface. And when we have the polymer and the rough surface together, we can get even more enhanced properties, and we haven't found anything that can stick to that surface. So in particular, we look at things like tomato ketchup, mustard, sauce, nothing will stick to this surface. It all runs off.
Okay. I think in the splitting of water, you use the Nafion membrane.
We did.
Is to transport the hydrogen
Yeah,
ion.
we have a Nafion membrane. It maintains a balance between the two sides of the cell.
Nafion membrane is very expensive. Do you have any other alternatives?
At the moment, we don't, because we've stopped that project. But I think if we were to go on, we would look to come up with another form. Yes, you're right. It is quite expensive.
So my question is relevant to your water splitting part.
Yep.
So what was the exact nature of your catalyst? Was it pure anatase and rutile, or
No,
there was some co-catalyst?
We've had a 3-year project to try and come up with the best possible catalyst. So we've looked at a whole range. Typically for us, if it's titanium dioxide, an anatase rutile mixture works best. However, we've also looked at visible light photocatalysts. So we've made nitrogen dope, phosphorus dope, sulfur dope, titanium dioxide. These are coloured materials. What we found is when we make a visible light photocatalyst, it does give you visible light activity, it turns over, but you lose some of the UV activity. And the net best catalyst, if you're using sunlight at the moment for us, is still titanium dioxide. We've also developed some other materials like boron phosphide, which we haven't published yet, but they show they've got a much shorter band gap, much narrower band gap, and they do work quite effectively. They have a good effect, so they tend to work.
So because I'm more interested in titanium oxide, because I myself work on titanium oxide.
Yeah,
and to my understanding, if you don't have a co-catalyst, you don't see much activity for water splitting especially.
For our systems, they've actually worked quite well, to be perfectly honest. We're doing most of the water splitting has been done in sacrificial systems.
Okay. So.
We have also added. We don't do it with a bias. A lot of people, when they do it, you add a potential bias between the anode and cathode,
Yes.
and that gives you a further kick to help the photo reactions. We don't tend to do that. What we have done, you're right, we do add some catalysts into there as well. So we do add a small amount of nickel, for example. Occasionally we've looked at platinum, but that was too expensive. But we've had a small amount of nickel embedded as filaments inside of the material. And that helps the catalysis, but it also helps the electrons to get out from the titanium dioxide layer and go to the other side.
Oh, thank you.
I'm sorry, gentlemen, we have to stop and thank Professor Ivan on his informative lectures. We are a little bit behind the schedule, and also we are extremely sorry about starting the lecture a little bit earlier than it's supposed to be, because Professor Parkins, he has an airplane, I think, to catch up. So we wish him a good luck.
Thank you.
Thank you. Dr. Abdulsalam will talk about the application of nanomaterials for environmental remediation. Please.
Thank you, Chair, for introducing me. Thank you for everyone for being here. Today I'm going to talk about nanomaterials and their application for environmental application and many more things. As all of us knew about that, nanomaterials are outstanding materials. that found its way around us recently because of their outstanding properties, extra surface area, reactivity, and so on. For that reason, a lot of research and industrial application are now focused on their, the use of nanomaterials. My research group and collaborator, we work on the sciences characterization of different nanomaterials and their application in different fields, based mainly on carbon nanotubes, nanographene, metal oxides, and nanoclays, and their composites. My research group focus on environmental remediation. We published during the last 7 years around 29 publications on environmental remediation using nanoparticles, nanomaterials. We work on corrosion protection using different nanomaterials for the corrosion protection of different steel structures. Work on hydrogen fuel cell. Work with the nanocomposite preparation and mechanical properties. We enhance the mechanical properties of different polymers using nanomaterials. And most recently is toxicity, because like a lot of us working with nanomaterials without know the bad side of it. So we explore the bad side of nanomaterials. We found that in different applications, it depends on the way you manufacture them and the ingredients you use. Sometimes they are bad, sometimes they are good in terms of toxicity. Today I'm going to talk about the environmental remediation. So one of the problems around us now, which is threatening the life of not just mankind, but all living organisms on the earth, is pollution. We have different types of pollution around us, like air pollution from the heavy industry that we use, water pollution affecting us a lot, soil pollution, and so on. So one of the things is how we can remediate the environment after to get polluted. Research scientists worldwide try to contribute to answer this question through different research, focus on the getting new method for environmental remediation, such as catalytic degradation right now, electrolysis, oxidation, biodegradation, and adsorption. One of the important things, unfortunately, is most of these methods have many disadvantages, just as the cost and the low efficiency and recycling problem and so on. So one of the important things is how we can find a method or prepare a procedure that we can use it for different environmental remediation with high efficiency and low cost and so on. So this is one of the questions most of the research scientists try to answer. The hypothesis of my research based on how can we use the nanoparticles for environmental remediation, and to answer that question, I will go through different things. My research group focus on the preparation, characterization, and application again of nanomaterials for environmental remediation in different pollutants. We study the different environmental factors that are affecting the removal process or remediation process, as well as PhysChem. We have to study the thermodynamics and the kinetics of the process itself. Today I'm going to talk about 4 of my recent publications with my group. First one is the sense characterization of novel manganese oxide. This novel manganese oxide, we prepared it at the lab by accident, and we found to have very, very good properties. It is actually in the form of nanocoral, as you can see here. Okay, this is the scanning electron microscope of the nanocorals manganese dioxide that we found. We characterize them using XRD to figure out what kind of manganese oxide. And when we do the term, they are in the form of fibers that combine together to be like nanocorals this way. And we use this nanocorals, this is the XRD, to figure out what kind of manganese oxide. This is MnO3, it's a mix of manganese oxide. We measure the surface area of them, have high surface area, around 170 square meter per gram, this manganese oxide. We use them for adsorption study to remove methylene blue as an example of organic pollutants from the environment. Methylene blue is very easy to work with inside the lab, and most of the, when we have a new material that we would like to know if it works or not, usually we use the methylene blue. Mostly the removal of methylene blue using the manganese oxide nanocorals is very fast, within a few minutes, and we studied the removal process from the kinetic point of view. We found follow the pseudo first order kinetic model, and we studied the kinetics of the removal process. We found most of the removal process is endothermic in nature, increased by increasing the temperature of the solution. The entropy was positive, which the delta G was negative, and that indicates that the driving process for the removal or remediation process is the entropy. We use the manganese oxide many times in removal of the methylene blue as an example of the organic pollutants from different real water samples. We collect wastewater samples and real water samples to see the efficiency or the applicability of this manganese oxide nano corals for the removal of methylene blue, and we found the efficiency is very high, almost like 100%. And we can use this manganese oxide many cycles, many times. We use them for adsorption, and after that we do desorption and study adsorption again. And we found that up to like that we try 4 times, we can use them with the same efficiency also. We use the same manganese oxide nanocorals for another thing. The first part here was focused on the environmental remediation of aquatic environment. We use them as well for the environmental remediation of the air environment. Okay, we use the manganese oxide nanocorals for the remediation from carbon monoxide. Basically, we change the carbon monoxide, which is toxic gas. We change the carbon monoxide to carbon dioxide. We studied the I don't know if it's clear or not. This is at different temperature. When we increase the temperature, the removal it's not. This is almost 1%. You have to believe me. Okay. Okay. When we increase the temperature, the conversion of carbon monoxide to carbon dioxide reach around 100%. Okay. And again, we oxidize the carbon monoxide to carbon dioxide. Carbon dioxide is more friendly, like can convert to many other things. But carbon monoxide is toxic gas. Okay, and when we increase the amount of the catalyst itself, the manganese oxide, we can get more conversion of the carbon monoxide to carbon dioxide. This is for the air protection. We use the new emerging nanomaterials, nanographene, for the absorption of nitroaniline. It's another one of the environmental pollutant, organic pollutant. Nanographene exists as nanoplates in nano size dimension, and we measure the dimension of the nanographene using different techniques like sorry, what?
لو سمحتوا يا اخوات سكروا المايك اللي عندكم عشان تسمعون.
We do characterization for the nanographene using different characterization technique like TM or STM to figure out what is the dimension of this nanographene, and we use them for the removal of nitroaniline as one of the organic pollutants in the aquatic environment. We studied the kinetics same way, and we studied the thermodynamics, and we figure out we can use the high surface area nanographene. Surface area is around like 700 square meter per gram for the removal of different organic pollutants from the environment. And it followed from the kinetic point of view, it follows the pseudo second order. Again, thermodynamics of this one, it's exothermic, which is the most favored one. Exothermic means like it requires less energy, less heat to remove the organic pollutant from the environment compared with the manganese oxide. And we found the efficiency of the removal is very high compared with other things. And basically, for the high surface area nanographene, based on the pi interaction with the surface of the organic pollutant and surface of nanographene itself. I will talk about different thing now, which is the catalytic degradation of the nitrate ions. Nitrate ions is one of the inorganic pollutants exist in water, and we use the iron nanoparticles, zero valence iron nanoparticles, for the degradation of the nitrate in the environment. We change basically nitrate ion in the environment to just nitrogen gas. The way we do that, we use zero valence iron nanoparticles. one of the problems that associate with the zero valence iron nanoparticles, I will just show you, I don't know if it's clear or not. Zero valence iron nanoparticles are very reactive. Once they exist, when we prepare them, they get oxidized by the air or water and change to regular iron oxide. And to decrease, would like actually to increase the activity, and at the same time we have to maintain the stability of the iron nanoparticles. So what we try to do, we stabilize them by using different support materials. We use nanographene as supporting material. We use carbon nanotube. We coat the iron nanoparticles with copper, and we support the iron-coated nanoparticles that coated with copper on the multi-wall carbon nanotube. This is the surface area of the different composites that we have, starting from the zero valence iron nanoparticles to the last one, which is supported on carbon nanotube. This is the transmitted electron microscope of the iron nanoparticles supported on the nanographene. I'm just presenting a few things about that. As you can see, the graphene nanosheets exist as a plate, and the iron homogeneously distributed over the graphene nanoparticles. One of the problems, again, of the iron nanoparticles, not just the chemical stability, not just oxidized to iron oxide, but as well they are magnetic materials. So once you are adding them to water or a solution, they agglomerate together, and it's not easy for them to decrease their activity. So when we support them on a carbon-based surface like that, they are not agglomerate, they are distributed homogeneously around the surface like that. This is the XRD for the iron nanoparticles itself. It have different oxide forms, iron 2 and iron 3. And when we support them on the graphene, we have just iron, zero valence iron. Iron exists in the elemental form. We studied the efficiency for the degradation of nitrate using the different nanoparticles that we have. We found that the iron coated with copper supported on carbon nanotubes have the highest efficiency compared with just iron nanoparticle itself. Here we use 5 milligram, and here it's 5 milligram, almost the efficiency when we use the iron coated particles supported on carbon nanotubes, almost it's 100% more compared with the original one. We study as well the effect of the ultrasonication, because one of the limitations of the process that it takes long time in order to reach to equilibrium, few hours, around 12 hours. When we ultrasonicate the solution, we can reach to equilibrium within around 120 minutes. So we can shorten the time of the process, remediation process, so much just by doing ultrasonication. We study the removal of nitrate ions from different environmental samples collected from the environment around us, like Red Sea water, wastewater, and water well, and those are containing a lot of nitrate. When we use the iron nanoparticles, that is one with the optimum one, we can reach to around 90% of the removal of the nitrate exist in the environment. The last one, it is not related to nanoparticles, but it was interesting study that we did, depending on the area around us. In Jeddah here, we have a sacrificial lake that most of the sewage we dumped at this area. So what we did, this is the sewage lake. This is called the Mesk Lake. Okay, we collect soil samples from the soil around the lake itself. This exactly the lake, and this is a little bit far, and this is at residential area, way far from this one. So what we did, we measured the concentration of different heavy metals ions on this soil surface. Okay, and we found good correlation between the distance from the lake, the main one, and the far and the farthest one. The concentration decrease as we go from one to another one. Okay, we found good correlation for arsenic, for cobalt, and for mercury, and those three are well known as very toxic heavy metals. We studied the removal process, again kinetically and thermodynamically, and we used leaching process. We used a solution of hydrochloric acid, diluted hydrochloric acid, in order to remove or leach most of the metals out of the polluted water, and it worked very well. We studied the kinetics and thermodynamics again, and we found good correlation for the remediation process. So in conclusion, my work we found that nanoparticles can be used prepared at normal condition at the lab, and this is one of the important things, as well as nanoparticles are promising materials that can be used for environmental remediation of different environment around us. And I would like to thank my collaborators at Mansoura University in Egypt, Carleton University in Ottawa, Canada, Beykent University in Istanbul, Turkey, National Laboratory of Frascati in Italy, Institute of Catalysis and Petrochemicals in Spain, Madrid, and right now as well, like, we're looking for more collaborators. And at the end, nanomaterials, we can handle them in very easy way, but we try to just be safe with them. Thank you so much for attending.
Thank you very much, Mr. Abdel Salam. And the floor is open, yes?
Thank you for lecture. But I ask about for theoretical, is it okay for removal for these heavy metals or environment, but practically for carbon monoxide examples, how to remove this carbon monoxide from outside or from environmental?
What usually we do for such thing, like we pack the material itself. Right now we are filing patent about this one in particular. You put it in like a column, like a filter, and when you pass the air through it, it just converts from carbon monoxide to carbon dioxide. It's the same like if you knew about the three-way catalyst that inside your car, and everybody's car, we have a three-way catalyst at the exhaust tube that convert all the exhaust gas before it go to the environment to normal gases, like NOx, for example, and such thing. So mostly it's not, you don't have it as just a powder in the environment. It's in a certain form, like a pack or a column. Same like the filter we use it at home for water.
For industrial?
They use it the same way. It's a filter. It's a filter. Yeah, it's a huge filter for industry, okay, or a little filter for regular things. But for industries, use it as like if you expect your industry producing a lot of carbon monoxide, you will have a huge filter at the end of the chimney. So all the carbon monoxide goes out, converted to carbon dioxide, basically.
Thank you.
Yeah.
Okay. Yes.
Thank you for this good lecture. My question is about how the recycle of magnesium oxide. How can we recycle it? Because sometimes we remove the methylene blue or any pollutant and then it present on my support.
Yep.
So nothing to do with it.
We have different techniques used for the recycle of the, if we call it adsorbent or a catalyst, when it comes to organic compound, for example. Like one of them, if you increase the temperature of your catalyst or the adsorbent in an oven till the temperature above the boiling point of this, degradation occurs. This is one of the things. Or this one good thing about adsorption is that we can recycle, we can get the pollutant again. Because in other study we use this solid adsorbent as solid phase extraction, so we can get back the pollutant or the analyte again from the solution. We do that using different solvents. Like if you add, like for example, acetone to your manganese oxide that have or absorb the methylene blue, or the methylene blue will come out. Okay, so it's one of the things we use for recycle all the time.
Ladies section, any question from there?
Yes, Professor, your adsorption of nitrate on zero valent iron or methylene blue in manganese oxide, are they physically absorbed or some chemical absorption?
No. When it comes to adsorption of methylene blue, it is physical absorption. The other one, when it comes to the zero valence iron, it is what we do catalytic reduction. We change the nitrate ion to nitrogen gas at the end. So we do chemical reaction. We use iron zero valence iron as a catalyst at that time. Just do complete degradation. It's not physical one.
Thank you for a very nice lecture about this, and it's good news to hear that you're filing a patent for that to remove carbon monoxide. About wastewater treatment, you mentioned something about hydrochloric acid or something.
We use the hydrochloric acid for soil remediation.
I didn't understand that very clearly about it. How that is to be treated before it that go to soil or whatever.
What they do actually, it's one of the techniques. They use it for remediation of polluted soil, not regular soil. Like, you know, like most of the cities right now is use dumpster. You know, they have certain area where they dump all the, unfortunately, all the garbage and everything inside, and they bury it. What happened is this, under this temperature and pressure, what happened is leaking of this pollutant from the environment, from this area to the other soil. And that's what happened in this case. Like the heavy metals immigrated, moved, transported from the lake to the area surrounding. And that's what we have seen at the presentation here. Like the concentration of the heavy metals is different. This is very high at the lake. And when we go out from the lake, it decreases. Okay? So one of the things they do for the soil as a remediation solution, they wash it with an acid, okay, or they wash it with complexing agent like EDTA, for example. What we have, that was the second, like we're working on that. What we do, we have now the acid, hydrochloric acid, okay, contain heavy metals. So we have to get the heavy metals out of this acid. For that reason, we're still working on that. We use nanomaterials to extract the heavy metals back from the acid one, from the hydrochloric acid.
Oh, that's good.
Yeah,
It's just to bring a new idea about how to dump our rubbish without to dumping like another. It's in a wrong way.
Yeah,
okay, thank you for that.
We don't solve a problem and create another one. No, no, try not.
Thank you very much, Dr. Abdul Salam. And we are moving to the second lecture by Al-Anud Musa Al-Asiri. Is she around? Al-Anud?
Yes, I am.
العنود انت جاهزة؟
أيوة دكتور.
يلا نبدأ. عندكم حقة؟ عندكم فلاش حقة؟ Our second speaker, Al-Anud, she will speak about dispersion of chemical toxic pollutants in atmosphere, a chemical security approach.
They prepared the presentation. Just a minute, please.
بقينا واحد بس.
اسكرها اطلعها بس عشان ما يعمل صوت علق عليك نعمل كفر تساعدنا انتم هنا ولا هي؟
يا العنود انت جاهزة؟
عفوا دكتور بس ينقلوا لي البرزنتيشن لكم هم يعملوا الكونكت.
البرزنتيشن حقه وشو يعني ايش؟
مطولين، نبدأ بأحد المحاضرين الموجودين عندنا يا العنود.
لحظة دكتور، بس كان عندنا تكنيكال بروبلم.
بس هل الرابط بيصير من عندكم ولا من عندنا؟
لا من عندنا كريم. اوكي ناو وصل عندكم؟ من عندكم دكتور.
ما هو موجود.
هو مو بنقول لكم يا دكتور مو واصل.
لحظة يبغى يشوفون واحد يعني. يلا ابدأ يا العنود، بارك الله فيك.
بسم الله الرحمن الرحيم. I'm العنود العسيري, researcher from Naif Arab University, Security Science in Riyadh. Today I'm going to talk about chemical industrial essential, chemical terrorism threat, scenarios, potential source, and chemical security activities. Actually, all of us, we work with chemical substance, so we must know why we need chemical security. The potential dispersion of chemical toxic pollution in the environment causing release of hazard or toxic material from industrial facilities such as petrochemical plant, oil and gas transport pipeline, and many other industrial activity in the event of malicious action which has severe security, social and economic consequence. Chemical security is it the prevention and detection of and response to thief, sabotage, and authorized access, illegal transfer or other malicious acts involving chemical material, other related substance or their associated facilities. Chemical safety, the achievement of proper operating condition, prevention of accident or moderation of accident consequence resulting in protection of worker, the public, and environment from endochemical hazard. Security safety concerns. Security is concerned with the malicious actions by humans that could cause or threaten harm of other humans. Safety is concerned with the broader issue of harms to human or the environment from a chemical hazard, whatever the cause. Actually, chemical terrorism possibility can be, but chemical materials have the potential to be used by terrorist group as a weapons, as their weapons of a mass destruction or a mass disruption. Chemical discernible disease, which give CDD, disperse the chemical materials into the environment. For example, of that, dirty bomb attacked on a chemical plant, chemical establishment, or chemical material or a transport. When using improved chemical explosive device, chemical discernible device, any method used to potential drips chemical material to create terror or harms. Like the example we told, the dirty bomb. It is made by packing explosive like a dynamite with the chemical material to be dispersed with the pump off. Generally, it can happen only in a cover determined area undetermined number of fatal cases. Distance of source to significant contamination. CDD not expect to travel afar, hundreds of meters not many. The industrial complex may travel hundreds of meters to miles for source. Generally low concentration at a distance, snow, rain, or all impact, will impact. The weapon impact from hundreds of meters to miles. Chemical terrorist threat scenarios. Theft of chemical webs, theft of chemical material to make any improved chemical explosives, theft of other chemical material, sabotage. The target, chemical webs, chemical industrial complex, and chemical materials. Facts. Intelligence data reveals that terrorist groups has experienced an interest in acquiring chemical weapons and CDD. Many successful chemical attacks has according to that, like what happened in India or China or Japan. Loss of control and malicious uses. Consequence of potential level of harms to individuals, public, environment, state, and international community. Consequence of a major incident, for example, what happened in a Popial accident. Similar consequence for malicious use of source. The worst industrial disaster the world has seen that happened in India in a Bhopal gas tragedy. It happened at one morning of December 1984. There is a large amount of water brought in a chemical storage tanks in a UK factory, where there were interaction with the tons of methyl isocyanate happened, which led to the high pressure and temperature, and leaked a large amount of a gas. Then the sky covered with a large toxic cloud. The people was wake up with the many disease and the lost eyes, and there is a lot of dead people. Where there died nearly 4,000 people in a sense of a begin of this gas in the first hour. Then retained the soil and atmosphere remains of a chemical for many years, that's making the waste capable of increasing death and injury according to government statistic. After that tragedy, with a quarter of a century has been the purge of UK by Dow Chemical Company in 2001, with a several of the legal problem and related to the factory, which was called the local state government responsibility to continue the clean up of that waste. This is the way of happening, and this is description what happened in that. The victim, like what we see, there is a lot of people lost the eyes, and there is a lot of something happened. The chemical theory, the water which directly introduction into in the gas tank cause a missing pressure that result exothermic reaction and final the explosion. This is the plant when the methylamine react with a phosgene, then they give us the product methyl isocyanate, which is again react with 1-nephthol to yield the coupling. Lesson learned from this disaster, we can see clear the cause of the disaster is a chemical event. It is impact continue to the day. So we must know there is no safe chemical substance. Consequence, Popial accident illustrates consequence resulting from unintentional acts involving source. In this case, loss of regularity control. Similar consequences could result from malicious act involving a source. Other potential consequence, environmental, economic loss, psychological and legal. Chemical weapons are super killer. Countermeasure chemical security, prevention, detection, right, we will, like where we go, and response to compact, theft, support, unauthorized access, illegal transfer, or the malicious acts involving chemical materials or associated facilities. Security and physical protection. Intend to prevent malicious acts by inside or outside enemies that may endanger the public or the environment. Program for security and physical protection for a chemical activity, materials and facilities need to be provided at all the time. Chemical security requires the involvement of effort and commitment of all organizations involved in planning, decision, concentrating and operating chemical plant. To be effective, it is critical to knowledge the importance of the chemical security and embraces chemical security culture. The first thing, operator level, a commitment to have a chemical industry includes a commitment to attempt to prevent any malicious acts. A commit to obtain a strong security culture should be established prior to make commitment to get chemical activity. Acknowledge of the recommend for security and physical protection and the identification of necessary legislation provide recognition of the commitment. The other step, state level, laws, regulation and authorized security requirement of the industrial unit, protection requirement and patent from malicious acts, illegal trafficking, careful selection and qualification of staff, establish design-based trade, defined anticipating consequence, confirm security culture. Implementing the definition for target, approval DBT, design of physical protection system to protect target from DBT, concentration testing and acceptance of physical protection system, acceptance of the operator security plan by the authority, training of ground and operators, training personnel to prevent the illegal traffic, development of physical protection and development of agreement of responsibility, coding of response to emergency or malicious organ excerpt. Chemical security plan, control on materials regulatory system, protection of materials, facilities, transport from that and sabotage, collecting and arrangement information on need, response of chemical security, incident, information security, coordinated with other state and international organizations, security at a major public event, chemical security culture. Security equipment, detection and monitoring equipment, police, road police, custom, physical protection equipment and chemical facilities. Conclusion, chemical industry is a major activity require careful planning, reputation and estimation in time, money and human resource need at stable political, economic and social environment. Any malicious act will endanger the public and impact the community. Necessity of in-chain control and security of chemical plant and chemical material. Chemical webs are an imprint potential source of a danger. All that stays the need for chemical security. Thank you.
Thank you, Anid, on the information. And any questions? Because we are a little bit late, we will go to the last speakers. Do we have a last speaker here? Huh? Okay, there is no more speakers. Thank you very much. Thank you very much for your attendance. And now it's time for lunch and prayer.
And adjunct professor here at the chemistry department. He has published more than 400 original research articles and supervised more than 70 PhDs and MS students. He serves a member of the board in many international journals, and he is a recipient of several awards, including the Turkish Scientific and Technological Research Council, Young Investigator Award, and the Society of Polymer Science, Japan International Award, the Elim Khan Foundation Technology Award 2008, and the Islamic Countries Technology Council Science Award 2010. He is also a member of the Turkish Academy of Sciences. His research interests involves the synthesis of complex macromolecular structures, photopolymerization, controlled living, polymerization methods, high-performance thermosets.
Thank you very much for your kind introduction. Well, in fact, my research area is not related to directly environmental scientists. I am a synthetic polymer chemist of all kinds of polymerizations, but I was asked by Professor Asri to talk something about environmental chemistry. Therefore, I selected our recent research combined with environmental applications. Then the type of polymers involved here are the thermoset polymers. During my talk, I will give information what thermoset polymers and polybenzoxazine chemistry, how we obtain from different sources, and then I will talk about mercury removal by using these materials and electrochemical manipulation of dismantling of the polymer films, copper removal by thermosets, and also the use of elementary sulfur there. So the thermoset polymers are shown here. In fact, they are cross-linked materials, and you cannot shape them by heating. For example, the tires of cars are kind of thermosets. Once you give the shape, you cannot reuse them. You have to either destroy or use as fillers and so on. Whereas thermoplastic polymers with different topologies, they are soluble and you can reshape them. But we wanted to make use of some thermoset polymers. This class, polybenzoxazines, we have written a highlight article in Journal of Polymer Science describing this chemistry here. In fact, these materials are replaced the bakelite, you know, as a typical plastic, but they are not really very good anymore. So the benzoxazines are used now in high-tech applications. Boeing and Airbus companies are trying to use it, they pass the test and they can be thermally stable up to 800 centigrade degree, but it's difficult to change the production style, which is expensive. They are still considering to use them. And you can use it even some other applications, high-tech applications in the area. These materials are cheap in the meantime. If you have a phenol, formaldehyde, and amine, one can easily form this benzoxazine ring. This benzoxazine ring undergoes polymerization without any catalyst. Just heating it, you have a network formed. And it gives molecular flexibility. You can change the phenols, you can change the amines, aromatic or aliphatic amines. It gives you a wide range of molecular design flexibility. So the chemistry is, as I told you, if you heat it and you have a polyphenol like bakelite, phenol, formaldehyde resins, you can prepare them. Even monofunctional ones, because of the possibility of forming by heat, there is a bond breakage, and this bond breakage causes the formation of cation, which essentially may attack to these positions or in bifunctional one here, and you end up with the cross-link ones. These are useful, as shown here, maybe the polymer or any functional group here. So you see that you can further use them if you have such phenolic groups. These phenolic groups can be reacted with isocyanates to form urethanes, polyurethanes. It gives possibility to have a composite materials, or you can cure epoxides with these ones. And they have advantage also due to the non-bonding electrons and hydroxyl groups here. There are strong hydrogen bonding. Despite the fact that there is a phenol group, they do not absorb the water at all. So these materials are really interesting. Besides, the polymerization is ring opening. There is no shrinkage. Any monomer, when you polymerize, the volume is shrink. Therefore, you cannot shape them as you expected in the beginning. But with this one, no volume shrinkage, low water absorption, high TG, no catalyst, no byproducts. There is an atom economy. And they are thermally stable for the fires and so on. Therefore, they have a very good properties. But they have some disadvantages. They are brittle, weak, film-forming properties, low processability, and so on. In order to overcome such problems, we made some strategy that you can combine with polymers. We published many papers in this area. Some of them are shown here. You can attach at the chain ends or side chains. These represent benzoxazine rings. You process because of the polymeric nature or main chain. When you heat these polymers, you have a cross-link material with high thermal stability. So I will show you some of them. You know, the click chemistry is very popular now. Alkene azide forms a triazole ring and benzoxazine ring is attached. This is polyvinyl chloride. Even the windows are PVC windows. So if you increase the thermal stability, it would be advantage. Or rubber, polybutadiene, you can attach this to the chain and you will be able to increase the thermal stability. Look at the polystyrene case. You see this is a linear polystyrene. This is cross-linked polystyrene, whereas this one is benzoxazine attached polystyrene. You see the thermal stability, even after 500 centigrade degree, they are still stable and the char yield is high. Same thing applies to PVC as well. So we did some other things. One can do even more coupling reactions. As in this case, we had a main chain polybenzoxazine. As you see, it's benzoxazine rings are placed on the chain, and you can eat them, maybe prepare desired many other things, as in this case fluorinated ones. These are even better for the hydrophobic nature and some other anti-fouling applications. As I told you, they were not processable. We wanted to make a liquid one. As you see that these are liquid, and just you form on a shape of the material you wanted to have, you heat it and you cross it. Moreover, you can have a kind of polyester through these hydroxyl groups here, main chain polymer as well. And you see, as we have presented here, these are flexible. It's a very nice material. You can heat it and cure it, and it's still in the shape of the initial production. We have also made further functionalization to have a main chain polymers possessing hydroxyl group in the system, and these hydroxyl groups give possibility to attach many other initiator functionalities, for example ATRP, polystyrene benzoxazine, or you can attach even photopolymerizable group. You have both from this side photocuring, from this side thermal curing. So we were able to increase the adhesion on the surface by attaching carboxylic acid groups here. As you see, the normal benzoxazine adhesion is very low, increased when the carboxylic acids are present there. And we went to the way more flexible by taking advantage of polysiloxanes. As you see here, the polysiloxane is a flexible material, and you see the thermal stability is really very high, even at 800, 900 degree, some percentage remains there. If you increase the siloxane unit, you can twinkle the material, it's extremely flexible. So we had a sulfone. Polysulfones are engineering materials, they are known. We attach these molecules into polysulfone systems. You can do another strategy. Sulfone is in the middle and the benzoxazines are at the chain ends there. So you can cure them nicely there. Clay is naturally abundant material. For example, in Tunisia, the clay is very nice and used many industrial applications. We were able to quaternize in collaboration with Japanese Professor Endo. This ammonium salt can be intercalated between the layers, and by adding additional benzoxazine, you have highly thermally stable polybenzoxazine clay nanocomposite. And we were able to show intercalated and exfoliated structures. This is exfoliated, this is intercalated, present in the structure. So maybe I should go, these new chemistries we introduced by thiols. I will move to some other applications, like I present here. You can do post-modification with thiol groups. If you have a thiol, any polymer or anything, even biomolecules, thiols, ring opening occurs with the benzoxazine ring, and it's not the usual thermal reaction. You can modify them easily. We were able to show the DSCA useful tool to check their ring opening reaction. The curing temperature from 255, it's reduced to 100 something. So you can do organogels as well. If you have the thiol here, this one will open the ring from here, and the other one with another chain, you have an organogel. You see it swells and it gets a higher dimension, and you can adjust the flexibility with the dithiol moiety. And we were able to measure swelling and also the mechanical properties of these materials. So in the environmental systems, we have to use materials as much as we can. If you just use and throw it, it causes environmental pollution. We are concerned about the self-healing of these materials. Benzoxazine groups there with the JEF-amine, polypropylene oxide in the middle to provide enough flexibility. And we have coumarin groups as well. These coumarin groups are photodimerizable. So they link to each other, form a cyclobutane ring as shown here. First we heat it and this benzoxazine ring opens. We have a coumarin groups in the network system. If you irradiate this above 300 nanometer, it will form a dimer. So if you cut a piece on the surface or something, irradiate this part by light, there will be self-healing. The damage will be unified again. Of course, this is a 2,2 cyclodimerization as we have presented here in the model molecule. Dimer is the initial one irradiated at 300 formed dimer. If you irradiate at lower wavelength, it goes back to original system. So this is another strategy we measured. Maybe I should go further there by again polypropylene oxide here and benzoxazine units attached here and some kind of coumarin group is there. This shows the chemistry there. As you see, we can follow the dimerization by UV absorption spectra. The coumarin moiety by irradiation, it goes down and there is new absorption developing. Once you form the dimer, you can have also adjust the going back system there. Again, it shows the photodimerization process. And how we measured, this was the case that we were able to show the self-healing. You see, we cut two pieces and we irradiated at this region here, and we were, if you pull it there, it will have still the original power to hold metal there. So it heals the damaged part by irradiation. This is another self-healing, to use materials more than their lives, or if there is a damage on the material, you can reuse them. So it's a kind of environmental solution to these materials. So in this case, we have again polysulfone this time, and benzoxazine units as well attached to here. When we make a film and cure them together and damage spacemen, by curing you see that there is a ring opening reaction of benzoxazine which can attack the polysulfone and it will cause a self-healing as well. In this case, we represented chemically that the carbocation formed here can attack the aromatic ring or so on, some polar groups. This is the reason to achieve self-healing. As in this case, look, this benzoxazine can attack here or even to polysulfone activated system, and so you have a kind of further cross-linking by thermal means. In this case, we show that the material is cut. If you heat with a gun, you have a recovery here. As you see, the initial mechanical properties after healing is not exactly the same as before, but there is a 60% healing in the system. We have also kind of autonomous self-healing. In this case, we prepared main chain polybenzoxazine, I will show you the healing chemistry as well. We put on the surface here thermal curing, and after heating their self-healing material, this is linked together, and you can see it can be expanded, still strong, and it's a self-healed material. Now we move to remove another application of environmental purpose. This is a kind of polybenzoxazine here, and it's a porous material. The surface is 1 gram, probably 500 square meter. If you have a solution containing mercury, if you add this porous system onto here, and it becomes clean material solution there, because the mercury as an interaction non-bonding electrons of oxygen as well as nitrogen, it's strongly coordinating. And the advantage here we have, you see that if you treat with acid, you recover back the original material. So it's a reusable one. It's selectively reactive towards mercury. We check the other metals as well. And due to the regeneration process I explained here, you see even after how many cycles, it keeps the activity to bind mercury ions in the system. So also when a material is used for coating applications and so on, we wanted to make something that you take out the material from the surface. This is called dismantling. So we have a kind of compound here, benzoxazine compound. You see quinone phenol structure here. Oxidized state is ketonic structure, and this is phenolic structure. So the oxidation reduction reaction may change. This is strongly adhered on the steel or any metal, whereas this one not. So we were able to make that this is a steel coated on the benzoxazine. If you make it on the oxidized state, it can come up from the surface without chemical treatment, just the electrochemical process. So this was a one-way dismantling and reusing the materials. Another concern in environmental system is to use renewable materials like vegetable oils and so on. We were able to prepare polybenzoxazines from modified vegetable oils as coating materials. Maybe the chemistry is too complicated here, but we were able to have nicely such systems. And these are, sometimes you need to have a strong adhesion on the wood surface for coating applications. So we made a scratch here, and you can see they do not peel off, and they are really good materials for wood coating with high thermal stability. I will talk a little bit about the copper removal. We have a benzidine-based adsorbent materials, and it has a high surface area, and you can measure it with carbon dioxide adsorption there. And you have in the water solution, where the water is contaminated with copper ions and so on. Again, the interaction with these molecules, you can remove from the solution copper ions easily. So it has a porous structure, and you see in the solution copper 2 ions is reduced concentration by treatment there, and we checked, this is a leveling of 100% is captured from the system there. So we have measured Langmuir friendly isotherms for this. I am not really familiar, but I can show you again, they are reusable. The activity remained the same throughout several treatments. And we have also melamine-based porous systems. You can see here they are networked, and they can, this is the original solution. After treatment, you go back to original by reuse. The copper interaction, again with the same materials, and we were able to show that they really interact with the porous material we have, and the infrared and other systems clearly provided this. And again, UV absorption, after 5 hours, the copper concentration is reduced. We defined the optimum pH concentration, and almost all coppers are removed from the solution. And this is the probably final part. You know, sulfur is most abundant element after carbon and hydrogen in the fossil materials. Therefore, you need to take it and make it a good use of it. It's byproduct of natural gas, petroleum refining, and they can. May I have some water from some? It doesn't matter. I can take from here. That's all right. Sorry about that. So the stored as massive deposits, mainly used in sulfuric acid production, but also in rubber vulcanization as well. If you expand the use of sulfur, this will provide a very good environmental concern. It's a melt processable. If you go to certain temperature, it melts itself. And therefore, it's a limited usage in industry. So what we did is to have a elemental sulfur together with benzoxazine. But it does not directly react with the benzoxazine. We attach a double bond to interact with the sulfur. So as we have heated together at this temperature, this is melted, and while there is a ring opening, sulfur reacts with the double bond. So we have a kind of copolymer, polybenzoxazine, together with sulfur. So it's a way to have a good use of elemental sulfur in industrial applications. So we were able to show that the sulfur bond, typical sulfur characterization, as well as benzoxazine formation. And besides that, the ring opening temperature of benzoxazine is come to rather lower temperature, which is advantage for the benzoxazine chemistry. And we believe that the lower temperature curing is due to the acid formation, because acids catalyze benzoxazine ring opening reaction. To prove that benzoxazine, sulfur, and silver nitrate solution, if the hydrogen sulfur is released, silver sulfide is precipitated. After heating, we saw that the color is changed, silver is precipitated. So we were sure about the mechanism of the polymerization. And we have another evidence that there are some bubbles on the surface, as shown here, but the smooth matrix material. So it's a very nice material that we have here. And we have again a high thermal stability. You can vary you can vary the concentration of the sulfur there. I would like to conclude my talk that benzoxazine chemistry is a very flexible chemistry. You can make a polymeric films, you can have a processable materials, you can have a self-healable materials, you can prepare a kind of ion binding molecules, you can make use of sulfur, which is a byproduct of many industrial things. So this is my group. I have some foreign students as well. This is from Macedonia, Nigeria, Iran, Japan, Ireland from Marie Curie Scholarship. And we have a World Polymer Congress in Istanbul next year, IUPAC World Polymer Congress. It's a beautiful city, and this is in the Bosphorus here. This is the Congress Centrum. It's Golden Horn in the near to historical part of Istanbul, and we have this is the Congress Centrum. It would be a very good occasion to see the many parts of Istanbul. So the Aziz Sancar is the this year's Nobel laureate. He is a Turkish originally, DNA recovery. He was awarded for 2015 Nobel laureate. Grabs is another Nobel laureate in early 2000 on polymerization, and Chris Matiaszewski, and these people are another plenary speakers, and we have maybe 100 invited lecturers in different sessions: environmental systems, nano systems, conducting system, electronic materials, etc. And by this occasion, I would like to thank you for your attention. Thank you very much. I am sorry I talk too loud, so the water in my mouth. Oh, thank you. It's very kind
Thank you,
of you.
Professor Yagi. If there are any questions?
Yes, please.
Thank you for your presentation. I am just wondering, because you make a lot of work,
Yes.
but you didn't focus about using renewable resources. For example, you can use lignin, for example, because lignin contains a lot of hydroxyl group. So I think it will be very good to use in preparation of benzoxazine. Second question about the last work of the benzoxazine with sulfur.
Yeah.
What about the mechanical properties after addition of sulfur? If increasing the mechanical or decreasing?
Well, we have not, starting from the last question, we have not measured the mechanical properties. We focused on the thermal properties, whether thermal stability is decreased. We assume that the benzoxazine has a very good mechanical properties, but less flexibility. But through sulfur, we may gain some advantages there. The first question is a good one, but I presented my own work here. But from Spain, Ronda and so on, many papers from castor oil, lignin and so on, even the double bonds of triglyceride oils, they have additional cross-linking. There are many studies there. So you can expand the benzoxazine chemistry to further renewable sources.
Comparing between the phenol formaldehyde resin and polybenzoxazine, the price.
The price, well, first in phenol formaldehyde resins, you need a catalyst. Here, no catalyst. These catalysts are more expensive, you put little. So we use phenol, the same price, okay? We use formaldehyde, the same price there. Only the amine there. So you can calculate yourself. This is commercially available materials. There are thousands of amines. You can vary the property by selecting the amine as well as phenols as well, but it cannot work with the aliphatic hydroxyalcoholic compounds. It has to be phenol there. So it gives much flexibility, but extremely better properties than the bacalide phenol formaldehyde resins. As I told you, really, this material passed the test for, not the inner part of the aeroplane, but the engine part, because 800 degree, the char yield is still good, and so.
Thank you.
You're welcome.
Also, my question is about mechanical and flexibility of polybenzoxazine compared to PAN, BVA, film or fiber.
Well, as I told you in the beginning, there are drawbacks of benzoxazine systems. They are brittle, normally powder. The first liquid one, we synthesized and published one. You can have introduced flexibility by having polymeric, any polymer system you want to introduce as a property to benzoxazines, you can have polyamines, like Jeff amines. You know, Jeff amines are flexible materials, so we introduce. So it gives you wide range of molecular flexibility depending on your expectations.
Bismillahirrahmanirrahim. Assalamu alaikum. Thank you for your presentation. I come from Algeria, at Tlemcen University. What is polyset with food?
With food? Nobody has tested yet.
I mean, yes, polyset on the water. You have in your hand.
PET.
Yes.
This is PET, and yeah, but it's not used for cover as an emballage for food materials, because it has a extremely high mechanical properties. So it would be waste to use for this purpose. But I can tell you that phenols, the consideration normally in polymers for environmental things, people say, is this dangerous for health and food? The main problem is, if there is a low molar mass compound, like monomers, additives, and so on, then these are dangerous, because they can migrate there. You just say it for PET, you know, for Coca-Cola, that they treat with Coca-Cola, the PET used for Coca-Cola with liquid carbon dioxide, because in Coca-Cola there is acid, carbonic acid, so it may dissolve the low molar mass compounds there. Therefore, it's different than the other systems there. We have not, to cut it short, we have not tested for food application.
Okay, and what you mean with that? Teflon?
Teflon.
Teflon.
Well, you mean, can you use Teflon to prepare polybenzoxazines and so on?
Yes.
Well, we have shown one example, fluorinated materials, not Teflon. Teflon is CF2, CF2, CF2. You need to have, in this molecule, additional amine groups to form benzoxazine there. But it's a good thing that one should think to have tetrafluoroethylene to have additional amine functionality. Then you can prepare benzoxazine easily.
Last question on the thermoset. Is the is the Duroplast family or another family? Thermoset, Duroplast family.
Well, when you say you cannot restrict thermoset description, any polymer that has network structure, you can classify as insoluble materials as thermosets. But now there is a new concept described with Ludwig Laepler that even thermosets, let's say this is bond here, if by external simulation you break the bond and react with the other one, then you can reuse like glass. When you melt the glass, it becomes viscous liquid.
Yes.
When you cool it, it's again solid.
Reuse, yes.
So this concept now is considered for thermosets as well. So reusable thermosets. We are working in this area as well. So
thank you.
You are welcome.
Okay, thank you again, Professor Yagi.
Thank you very much. Selamun Aleyküm.
Thank you, Mr. Chairman, for introducing me. The title of my talk is Modification of RO desalination membrane with hydrophilic polymers. I will start with a short introduction about problem definition, membrane types, reverse osmosis. Then I will introduce the equation, how can we reduce fouling, modification of membrane surface. I will show the results of our work, showing some characterization techniques and results of the modified RO membrane surface, membrane performance and protein absorption, and I will summarize my work and results in the conclusion. So the problem that the whole world faces is the global demand for water, for pure water. And mostly in some areas like Gulf area, Egypt and the Red Sea, USA, they are using now, they used to use thermal desalination for having pure water, but now they are using more the membrane modules, and they estimated that approximately 15.6 billion USD will be the cost of membrane modules by 2012. The market is expected to grow around 8% annually to reach 25 billion in 2018. So we have the problem is the lack of drinking water, which then needs, of course, desalination. We need to desalinate seawater or brackish water. But then we of course we use the RO membrane, and then we have the problem of the fouling and bifouling of the membrane after using. We have several types of membranes. They include microfiltration, ultrafiltration membranes, reverse osmosis, and nanofiltration membranes. The MF membranes have the largest pore size and typically reject large particles and various microorganisms. UF membranes have smaller pores than the MF, and therefore they are used in addition to the large particles. They also separate microorganisms. They can also reject the bacteria and the soluble macromolecules such as protein. The reverse osmosis membranes, on the other hand, are effectively non-porous and therefore exclude particles and even many low molar mass species such as salt ions and organics. The reverse osmosis membranes is an efficient method. This method is an efficient one for seawater desalination as a process. For the development of these RO polymeric membrane, a technique called interfacial polymerization for synthesizing a thin film layer on the membrane. In this method, a thin layer of polyamide is formed on the polysulfone membrane, as shown in the picture. So the chemistry or the interfacial polymerization is a reaction of the trimethyl chloride with metaphenylene diamine in order to produce a polyamide thin film. This thin film is of a thickness of about 100 to 200 nanometer on a polyester sulfone or polysulfone support layer, which is of a thickness of 40 to 80 micrometer. These two layers actually on a non-woven PET support, which is about 120 to 200 micrometer thickness. After using this RO membrane for some time, they suffer fouling and biofouling. So how to reduce fouling? We have two methods: the conventional method, which is pre-treatment of feed water or adding of anti-scalant, or modification of the membrane surface by turning the surface more hydrophilic, reverse the surface charge, use of aliphatic amines, or coverage of polyamide layer with chlorine stable polymer. So our strategy is the modification of the RO surface with hydrogels. As a hydrogel, we use the hyperbranched polyamide. We prepared it in a high molar mass, about 60,000 molar mass. The method can be seen here more in this schematic illustration. On the nonwoven, we put the support layer, and then we make the interface polymerization. Then after curing for 2 minutes, then we have the active polyamide layer. Between the curing step and the polyamide preparation step, we spray the polyamidamine solution, and then we make curing for 2 minutes at 80 degrees centigrade. We use two kinds of solvents. We use the polyamidamine solution in methanol, and also we used the solution of polyamidamine in water in order to investigate the effect of solvent on the newly formed membrane. Of course, since we used water or methanol as solvents, these two solvents, they have OH groups, and we are depending or relying in our action or work on the rest carboxylic groups on the polyamide layer. So there will be a competitive reaction between these hydroxyl groups of the solvents and the amine groups of the polyamidamine. So that we made the model compound, and here we can see the component ratios found in the model reactions with equal stoichiometry of water and N-butylamine, and we found that the most subunits obtained are for the reaction of the amine with the carboxyl groups. With the assignment of the atom types in aromatic polyamide groups of polyamidamine using XPS. We did this, of course, for the polyamide layer without modification, and then we did also this for the modified membranes. And in this pictures, we can see, or spectra, we can see the new signals for the carbons and the nitrogens. Of course, in the carbon, we can see more the newly the new environment or new groups for the carbon attached to the carbons of the polyamide groups comes from the reaction of the amine of the polyamide amine with the carboxylic groups. So this is a confirmation for our reaction or for our grafting process. The membrane morphology, of course, very crucial for our separation work after this. So we have to look at the surface of the modified membranes. So we have here the surface images. We can see that we can differentiate between the ridge and valley layers or shape in the cross-sectional images, but the polyamidamine too has a high and complete surface coverage with the new hyperbranched polymer. The surface roughness also showed that we have more, confirms the last result, and we have more of the polyamidamine on the RO membrane, more than this for the RO membranes modified with the polyamidamine solution in methanol solution. The surface properties also was investigated or were investigated using zeta potential, and here we can see that the membranes with polyamidamine 1 and 2 has a higher pH value, which means that we have more amine groups on the surface. And also we investigated the contact angle using the air captive bubble method, and we can also see that the UTC 70, which has a commercial membrane, has lower contact angle than the membranes modified with polyamidamine, which also confirm the presence of more amine groups or more hydrophilic groups on the membrane surface. Now we can investigate the membrane performance. The unmodified membrane exhibits permeability of about 0.71 kilogram per meter square per hour per bar, which is about 20% of commercial membrane. The modification, on the other hand, the modification with polyamidamine resulted in an increase of the permeability to 0.89 and 0.85 for the polyamidamine covered with for the TFC covered with polyamidamine 2. And the salt rejection also was investigated, and we can see that the unmodified membranes showed a comparable salt rejection of 98.2%. For the TFC polyamidamine 2, the salt rejection remained unchanged, 98%, while the TFC with polyamidamine 1 showed a slight decrease in salt rejection by about 3%. The protein absorption and the chlorine resistance. The modified membranes also showed lower protein absorption, and also we checked the chlorine resistance of the newly formed membranes, and we made filtration of 500 part per million hypochlorite solution, and it was found that polyamidamine is effectively acting as a protective layer. So as a conclusion, permanent and stable surface modification of TFC-RO membrane was achieved. Grafting of polyamidamine on TFC-RO surface is confirmed by XPS and SEM. Surface properties were investigated, also with AFM, zeta potential, and contact angle. The salt rejection of polyamidamine 2 membranes remained on a high level, which is comparable to the unmodified one, while with the polyamidamine 1 membrane exhibit a decrease in salt rejection to 95.5%. The protein absorption on polyamidamine 2 membrane was less than for polyamidamine 1 membrane and the unmodified membrane. And finally, chlorine resistance of the modified polyamide also was confirmed. So by the end of my talk, I would like to acknowledge my group in Egypt and also our partners in Germany, Professor Brigitte Voigt and sorry, her name is not here. No, it's still here. Yeah, Professor Brigitte Voigt, Dr. Mayerhab, Christian Klangler, and Daria Nikolova, and of course the financial support from SGF in Egypt and PMPF in Germany. And thank you for your attention.
Thank you very much, Professor Muna. I have time for one question, if there are any. Is there, when you use that coating, do you mean that you do not have to use any anti-scalant?
No, I think not.
You do not have to?
Actually, we did this work in lab, okay?
Okay.
And I don't think so. You don't need any. Actually, in the water plant, you need, of course, you make antiscalant before going to the membrane.
Okay.
And but for our work, we use water, distilled water to yeah.
Thank you. Thanks.
Thank you again, Professor Muna. Our next speaker is Professor Sheikh Ashraf Ali. He will be talking about synthesis of some hydrophobic cross-linked polymer acid for simultaneous sorption of organic and toxic metal ion contaminants.
Well, I am Ashraf Ali from King Fahd University of Petroleum and Minerals Chemistry Department, and I thank very much ICAC, King Abdulaziz University Chemistry Department, for asking me for giving me permission to come here and talk. Does it have to do anything with this? No. Okay. Oh, thank you very much. So this is where I am. I will be talking to you about synthesis of hydrophobic. I'm sorry. Oh, please come back. Oh, synthesis of. What is the point? Yeah, synthesis of hydrophobic cross-linked polydeuteranic polymers that will be used to remove metal ions and organic contaminants together. This is the hydrophobic part that will take care of the organics, and this is deuteranic part that will take care of the toxic metal ions. So I will be talking a little bit about the synthesis, and then I will be talking about their application. Now I will be using Butler's cyclopolymerization reaction. Please look at this diallylamine salt, which can undergo homopolymerization to give a linear polymer with 5-member ring embedded. It is the 8th most major architectural from architectural point of view, this is the 8th most important polymer. And this little gentleman has over 1,000 patents and publication by Butlers. It can also copolymerize with sulfur dioxide to give this alternate copolymer. You know, a deuterion is something which has plus and minus in the same repeating unit. And an amphylite will be one where plus and minus will be in alternate repeating unit. So look at this molecule, please. This is a amine group and a phosphonate. You react with this thing, you get this SN2 reaction, plus and minus. Now it becomes deuterionic. You polymerize them, it becomes polydeuterion. This is in Polymer Science we published. And this is here, you hydrolyze them. Then you see here plus, minus, minus, minus. pH responsive polymer we have synthesized and we have described their solution properties and many things. Likewise, we have copolymerized with sulfur dioxide, and you see here nitrogen is a ligand and these two oxygen, phosphonate. Another one is here, we have a zwitterionic unit, and this is zwitterionic anionic. And this is a polymer again synthesized. Now let me take you to this one that we talk about cross-linked. Now you see here, if you take this molecule and formaldehyde, you get this diallylamine salt. You homopolymerized and you get this homopolymer. Now here the beauty is that this nitrogen is, its valency is unquenched, means it can go back to nitrogen with lone pair on treatment with base. Okay, that's homopolymer, but we are doing a little trick here that we are using a cross-linker. So the polymerization can happen on both sides. Well, if it can happen on both sides, then we will get cross-linked. 3-dimension thermoset. And this one, after sodium hydroxide treatment, this is zwitterionic, it becomes anionic. This is a very good ligand, chelating ligand. This is the cross-linked polymer we first introduced into the literature, and with this publication, breaking journal articles, we use many other things and we utilize them for removal of chromium, lead, strontium, which is a byproduct cation in nuclear reactor. That is, we have shown them very effective removal of that. Now you see here, this is methionine ester. Here, this is one of the amino acids in our body. They hydrolyze the methionine. If we annihilate this thing again, it becomes a Butler monomer, and we polymerize this thing again. This beautiful 5-membered embedded polymer we get, we hydrolyze them, we get zwitterion. And then you take this methionine and with malic acid, and beautifully it gives ion pair, and it gives a very good alternate copolymers. We can see here, we hydrolyze them. This is a nitrogen ligand, CO2 ligand, sulfur ligand, CO2 minus, CO2 minus, all these things, many ligands. So we take this thing, we again do sulfur dioxide. Yeah. We again do sulfur dioxide, and we get a copolymer, beautiful. And during copolymerization, some of the sulfur is oxidized to sulfur. No problem. It imparts more solubility. Now please look at this thing here. We take here, this is aspartic acid, residue of aspartic acid. Beautiful aspartic acid monomer, 90% yield of this Michael addition, and you get this monomer and polymerization. You see here, this is the residue of aspartic acid. We have published in RSC Advances Reaction Functional Group 2015. Of course, we had application in mind. You see here, that thing, we add 5 parts per million in reverse osmosis, this chamber, and we use supersaturated solution of calcium sulfate, and we use 5 ppm of that polymer, and it can prevent precipitation for about 300 minutes, 5 ppm. Of course, the blank, it immediately precipitated. Because the conductivity, calcium plus sulfate plus becomes calcium sulfate, then the ions are not there, so the precipitation happens, so you see the conduction it decreases. This is blank. If you have 5 minutes, it's here. 10 ppm for 700 minutes, no scaling. Average 15 ppm, it keep on going for 4000 minutes. Now you need 20 minutes, just 20 minutes in the desalination chamber to do the job. That if the calcium sulfate precipitate, it fouls the membrane, it reverse osmosis membrane. So this is an example. Now look at this thing here. This is methionine, this is ethyl ester of methionine sulfoxide, and this is our monomer, and this is our polymer. 1, 2, 3, monomer, monomer, polymer. Now look at this thing here. For Aramco and others and pipelines, metallization and pipe protection, corrosion is the biggest problem. Corrosion loss is more than the combined loss of flood and earthquake. How does corrosion inhibitor works? It is the corrosion inhibitors of atom like nitrogen lone pair, sulfur lone pair, and this is the iron vacant d orbital. They donates it and protects the surface. Now I will show you one result. Remember that this is 1, 2, 3, 4, and here you are 1, 2, 3, 4. This is monomer, 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 polymer. I have never seen a polymer which at the level of 1 ppm gives 93% protection in 1 molar HCl 6 hours at 60 degrees C. I have not seen it. 1 parts per million of that polymer, it gives 93%. One of the best paper we published here in Corrosion Science 2014, we have been able to get for 5 ppm we used to get about 60% or 50%. But here it is 1 ppm. We have done this experiment about 5-6 times. You couldn't believe it that 1 ppm of that polymer with the sulfur gives you 93% protection. That's very nice. Now let me take you towards another thing here. You see, we have made a polymer cross-linked resin that has carboxylate, phosphonate, sulfonate, carboxylate with sodium hydroxide treatment, carboxylate, phosphonate, sulfonate, and it gives amazing performance in the removal of lead ions and chromium. It has many chelation center with different pKa value of the corresponding acid. So it's beautiful, it can be selective and it does beautiful job. I cannot present the work. This is 1/3, 1/3, 1/3, and the cross-linker is 7%. And it has 9 different chelation center, and that can do the job, and many selective job to remove chemical toxic metal ions. Now finally I am coming back to this point. Now you see here, this is made from glutamic acid, again an essential amino acid, cheap, plenty of available in the market, and here is the hydrophobe, 18 carbon, and I put them, this from glutamic acid, I put them here, and this is the cross-linker. The polymerization happens this way, that way, both it will happen 3-dimensionally, and it gives this polymers which has chelating points and hydrophobic moment. Now here I am, this is used to simultaneously remove chromium and a eriochrome black tea dye. It simultaneously removes dye and chromium, and 90% it is. We are very preliminary work we are doing. We have not published this one yet. Now this is here, it is a colored sample, and after treatment with this thing, eriochrome black tea is become clean with this. It is probably this hydrophobe is interacting with this aromatic compound, organic with organic, and they remove this thing. And that is the way we are here. Our polymer will serve dual purpose. One is to remove toxic metal ions, other to remove organic contaminants at the same time. And I thank you very much from the chemistry department of King Fahd University, Saudi Arabia, for inviting me here, for letting me come here. And I want to show you the best of East and Middle East. And thank you very much. I wish there are more people to see, and I have decided not to go to any conference anymore. Really, I mean it. And I am sorry, we are trying to do as best as we can with difficult situation. But I'm sorry. Thank you very much.
Thank you for your communication.
Yes, please.
From Morocco, the interaction with your material and the eyes, it's a strong interaction or weak interaction?
Oh, our materials with chelation.
With the ions, with chrome ions. With
This is a strong chemical absorption.
It's absorption, chemical absorption.
Yeah, chemical, physical. You see, they have chelation. It's a chelation. You have a nitrogen lone pair, you have a CO2 minus, phosphorate minus, sulfonate minus. So they chelate. They grab it.
But why you put your material between two phases? Two phases. Feed phases and rest phases. With ions, with chrome ions.
Yeah.
You observe the migration of ions or the fixation of ions? Why with your materials? With these materials. When you synthesize membranes, elaborate membranes.
Not membranes, it's a resin. Yeah.
When you put your resin between two phases.
No, we just take this resin insoluble. It swells and that 20 milliliter of water.
Because
20 milliliter water containing chromium, lead or whatever, and the dye.
Because with your works on membranes, with like this material, and with the solution containing chrome ions, mercury ions.
Yes.
It's not fixation ions, it's diffusion ions throughout the membrane. And
you can put it
with very not a strong interaction. It's a very weak interaction.
It is strong interaction. It is a chemical exchange. It's not a physical exchange, because you have a chelation point here. You see here. Sorry. This is you can just look at this thing here. You are having here is here. This is the most chelating. Is lone pair minus, lone pair minus, lone pair minus. It will just grab and chew the metal ion in a 5-member ring, 6-member ring. This is here.
Apparently oriented with your reason. This sites, this interaction sites. The interaction depends on the orientation of this site.
It's a beautiful 5-member ring. A metal ion comes here, metal ion comes here, metal ion comes here. It's beautiful geometry. It is beautiful. It has 8 different chelation stability because of the pK of so many things.
Thank you.
Okay.
Thank you very much again.
Thank you.
Thank you for that hard work you did with this material. When you did the job of removing the element and the organic compound, is that by the accident or you mean it from the beginning?
What? Yes, the question.
Okay. Because your material is doing the double job for removing element an organic compound.
Yes.
Simultaneously. Is that something you mean it, or just by accident you discover that your material?
No. We planned it. Yes, we planned it. We proposed it, and this is an STI project. It's a dual-purpose resin.
Oh yeah.
And it is a very initial thing. We have here this thing. We want to put more aromatic group here, and type of aromatic group, and that can do better jobs. This is just the carbon 18. You can take chloroacetic acid, chloroethane, bromoethane, dichloro, all this. They are organic contaminants, and this is the idea that it will do the dual purpose. This is amino acid, glutamic acid, the residue. Yes, it was planned.
Oh yeah, okay, that's fine. Yeah. And did you try the regeneration of the material itself, the resins?
Yeah, yes, please.
Regenerated.
Oh yeah, that is reason. You get 0.1 molar nitric acid for 30 minutes, and they clean everything out.
Oh yeah, okay, that's fine. Thank you. Thanks.
But I'm sorry, not only one or two people are saying this thing. I have come from so far distance.
That happens.
I don't know. I have done so much effort, and
because it's Kafsa, people say this is Kafsa.
No. This is.
We're supposed to have our last speaker, Professor Levi Melody. I don't think he's here, so we'll end this session.
Yeah, you can put it on.
And thank you.
Seal phone fax. Versus 5.